Hello students, in this video we are going to talk about the differentiation, the concept of derivative for a real valued function. So essentially we are assuming, I am assuming the function f is from omega, okay, and omega is a open subset of Rn to R, okay. Let's say that I am assuming that okay, here let me write it, omega is an open subset of Rn, subset of Rn, okay, and this is holds for any n greater than equal 1. And so we are assuming that the function in this video, at least whenever I am not specifying anything, is from Rn to Rm, let's say, okay, and where both n and m are natural numbers, right? So f is a function from Rn to Rm. And generally speaking, first of all, we will introduce the concept of addition. So first of all, we will introduce the concept of derivative, right? Derivative for a real valued function for f from omega to R, right? And once we do that, then we will see that we can do the exact same thing for Rn. So let me first of all introduce this concept, and then we will go to the other part. Now please bear in mind that all of these I am assuming that you have already known the concepts, but I am just this is kind of a revision in case that you have some gaps or in understanding, this will fill it up, okay. And also if you have want to study more on these subjects, of course you have the books by Rudin, math analysis, principles of mathematical analysis, that is, okay. I am not writing the whole book name, but you guys know Rudin, and you can of course look at the Apostol book, Tom Apostol book, okay. Tom Apostol, okay. This is also math analysis, mathematical analysis. So these are the two books which you can look at for these things. So let me introduce you the with the concept. So essentially, let's say f is from AB to R, okay. So this is motivation. F is from AB to R is differentiable at a point x naught which is in AB. What does that mean? This will imply that limit, so this is what we mean, right? Limit h tends to 0, f of x plus h minus f of x, okay, x naught minus f prime x naught times h by h. This is actually 0, right? This is what it means. Now of course the equivalent form of this, so basically you can actually see that this is equivalent to this, writing this is limit h tends to 0. So basically the this expression here is equivalent to this expression, that if I put a modulus here, nothing changes, okay, minus f prime x naught acting at h by mod h equals to 0, okay. If I do that, nothing changes. So essentially I am going to use this idea to motivate my definition of derivative for real valued function, okay. So definition. So please remember this, of course we can, the definition which I am putting it for a function from Rn to Rm, okay. So let me do it this way. So let f from omega, so again whenever I am writing omega, please remember that it is in subset of Rn, okay, to Rm is any given function, okay. Then f is said to be differentiable, okay, to be differentiable at the point x naught, clear. And where is x naught? Is a any element in omega. See here, omega open is important because we are basically looking at a neighborhood of x naught, right? And that neighborhood exists because omega is open, okay. So we are assuming that, okay, at x naught in omega, if, right, if there exists there exists, so I will write it like this: if there exists, this is the notation which I am using, okay, there exists a linear transformation. So we have talked about linear transformation in the earlier lectures, from Rn to Rm, right? Rn to Rm. So this is omega subset of Rn, right? So the linear transformation will be from Rn to Rm. Okay, so wherever omega lies, not necessarily from omega to Rn, Rn to Rm. Clear? Okay, such that the following holds. Okay, so this definition is motivated by our earlier this definition. Okay, this definition, using this definition we are writing this. So what is it? F of x naught plus h minus f of x naught minus h by the norm of h. So please remember so this has to be 0, this has to be 0. Okay, and so basically the a, so we say that a is nothing but the derivative of f at the point x naught. This is this is the notation which we use. A is basically df x naught. This is how we put it together. Okay, in many books you can also see it will be written like this, but anyways, since it doesn't really matter, we will write that it is capital df at the point x naught. Clear? Okay, now if it is differentiable at every point x naught in omega, then of course it is differentiable in omega, so that is always there. You guys already know that, I am not doing that. Please remember this, the modulus here, the numerator, okay, the modulus in the numerator, this modulus, the norm here is in Rm, okay, and the norm in the denominator, this is in Rn. Okay, and okay, now the thing is this, see, why I did not use this particular definition but I used this definition, because if I am using this definition without the norm h, it will not make sense, because in that case you are basically dividing out with a vector. Okay, so we have to use this particular definition. I hope this is clear why we did this. Okay, so basically what I am saying is the difference between the fx naught minus plus h minus fx naught can be actually approximated with a linear approximation. Okay, right, this is what it means, right? Now the thing is this, with this definition, of course we know that if the derivative exists, this is going to be, so small remark, so please check this, check that the derivative is unique, okay, so basically if it exists, it is unique. If it exists, of course, if it exists. Okay, and please remember that this a depends on the point x naught. Okay, so let me write it this way, this depends on the point x naught. Okay, so basically if you change x naught, a is also going to be changed. So this is not a linear transformation for all points in omega, right? For every point you have one unique linear transformation. Okay, so let me write it this way. Please note that for every point a changes. Let me put it this way, so you do realize what I am trying to say. Okay, so that is there, right? Now the thing is this, see, and we call it this we say as this is the total derivative, right? This is called a total derivative of f at the point x naught. This is called a total derivative. Clear? Okay, so now the thing is this, see, since derivative of the function, a function from Rn to Rm, okay, so that is basically a linear transformation to Rn to Rm. So basically let me put as an example what is the derivative of a linear transformation. Okay, so basically if you are starting out with the linear transformation, what should be its derivative? So as an example, let's put it as an example. Okay, so let f is a function from for now let's just assume that it is from Rn to Rm and is linear. Okay, is linear, and now the question is this, I want to put down that, and let's say, and x is a element in Rn. Okay, then I want to see what is a prime x. Okay, and essentially you can actually see that this is going to be a. Okay, so how is it possible? You see, what happens is a of x plus h. If you calculate this thing, a of x plus h minus a of x is, since of because of linearity, this becomes nothing but a of h. You understand? So this is nothing but a of h. So you do realize that a prime at the point x, this is definitely going to be a. Okay, so essentially here the remainder term is going to be 0. So essentially this is what we have. So basically, and you also expect it, right? Because you see, since it is linear, what is the best approximation of the function? The function itself, right? So that is why this is the case. Okay, now B, another small thing is this, that let's say f is from Rn to R, right? Rn to R. Now the question which we need to know, and this is important, okay, Rn to R, given by f of x, let's say x1 xn to be, let's say 0, no? Okay, or let's say any constant k, and k is a constant, okay, any constant k. Now the question is this: what is the derivative? Please check that the derivative. Please check that the derivative at any point. Okay, so df at any point x, this is going to be the 0 linear map. So basically, this is not 0 in Rn. Please remember, this is a 0, and 0 belongs to the linear from map from Rn to Rm. So basically, the map which takes every element of Rn to 0. That is the map. Clear? Please, you have to check this part. So please do that. Okay, now the question is this: what are some of the properties that we know? One of the most important properties which we use while talking about derivatives is the so-called chain rule, right? What is chain rule? So essentially, let me just write down the chain rule. Of course, you know how to prove it. I mean, you can do the exact same thing what you did in R1. So same sort of proof works. Okay, so let's say let omega subset of Rn. Okay, this of course I am assuming all the time, and f maps omega to Rm. Okay, f maps omega to Rm is differentiable at the point x0, is differentiable, let's say differentiable at x0 in Rm, at x0 in omega. Okay, so let's say it is differentiable at the point x0. Now you see, we are looking for another map G. So let's say G maps an open set containing f of e, containing f of omega, okay, into Rk, let's say into Rk. Okay, so basically what is happening is f is from omega to Rm and g is from f of omega to Rk. Okay, and g, we are also assuming that g is differentiable, j is differentiable at f of x0. So we are assuming this. Okay, now if this is the case, then if you define capital F of x to be g of f of x, okay, then capital F, then we can say that capital F is differentiable at the point x0, differentiable at x0, and what happens is, this is very, very important. Please remember this: f prime x naught is nothing but g prime at the point f x naught times f prime x naught, right? So in this case, what is happening is this: since f prime is nothing but a linear transformation, which again actually is nothing but a matrix, so basically it is a m cross n matrix. Okay. So another small remark before I move on to the other important parts. Let's do this small remark which I forgot actually to put it here. You see, if f is differentiable, so f from omega to Rm, okay, f omega to Rm, let's say, is differentiable at the point x0, right? Is differentiable at x0. Now you see, what is happening is this: if you so then what happens is this: you have this df, right? So df x0, this is a linear map from Rn to Rm. This is given, right? Rn to Rm. Now what do we know? Then we know that any linear map from Rn to Rn is basically nothing but a matrix, right? Then df x0 is a, you can actually write it as a m cross n matrix. Clear? Okay, now the question is this: how does this m cross n matrix looks like? That's the idea, and we need to put this idea together, that how does it look like, then we are done more or less. That's the okay, question which we need to answer. Okay, so to do that, what we are going to do is we are going to start with something called the concept of partial derivatives. You understand, it's the m cross n matrix, that's what we know, but we can actually, you know, for natural, for generally calculating the derivative, we actually need to know what exactly is the matrix, how do we compute something like this, and to do that we need the concept of partial derivatives. And please remember this, I am skipping a lot of ideas here, since it is assumed that you already know this. Okay, so what about partial derivative? See, essentially what we are doing is we are basically looking at derivative in a particular direction, right? Not in any arbitrary direction, but the unit directions. Okay, so what we have is this. Let's say that if, again, given f is omega subset of Rn to Rm, okay, is a given function. Nothing is given. We are not assuming in this case that it is differentiable. So for this function, let's say this is any given function, okay, and I am going to define the concept of partial derivative for any given function. Okay, so any given function, right? And now what we are going is, I am going to, as I told you, I am going to look at the concept of derivative in a particular direction, right? So what I am going to do is, I am going to choose a particular direction, means unit directions, okay, the basis directions. Okay, so let's look at the particular directions. So let E1, E2, E1, En and U1, Um be the standard basis, of Rn and Rm respectively, and Rm respectively. Okay, respectively. Now what happens is this, then you see, then f of x, if for any point x in omega, f of x will look like this, no? It will look like summation I equals to 1 to m, because you see f of x is an element of Rm. So there we will have m components, right? So it will look like fi of x ui, right? Ui, and this x is in omega. Clear? Okay, so for any x in omega, f of x will look like this. So it can be written as u1, u2, um, the linear combination of those, and those coefficients I am writing, of course those coefficients depends on x, I am writing it as fi of x. Okay, so therefore what do I have, what I wrote is fi of x is nothing but f x, okay, the dot product with ui. That is how you calculate what fi of x is, right? And this holds for all I between I to m. Okay, now the thing is this, with this idea I am going to define the concept of partial derivative. Okay, so what is the partial derivative? So for x in omega, okay, and I between 1 and m, j between 1 and n, okay, we define the partial derivative. We define. So I will define the partial derivative like this, dj fi of x. Clear? So basically what it means is I am looking at the jth direction, okay, jth direction, okay, of the component function fi. Okay, so that is defined by limit t tends to 0. So basically f1, f2, fn, these are the functions, right? You see, if you write it like this, what are see, fi is a function. So if you think of it, so see, note fi is a function from where to where, x is in Rm, right? So x is fi acts on an element of omega, right? Fi is from omega and the range is in R. Okay, so basically fi is a real valued function. Clear? So I am going to define for a real valued function, I am going to define the derivative in the jth direction. Okay, so this is defined by fi of x plus t Ej. Okay, so you see I am looking at the how f is changing in the jth direction and then fi of x by t. Clear? So how f is provided the limit exists, of course, provided the limit exists. So you do understand what I am trying to say. I am not looking, what I am doing is this. First of all, for a given f, you see given f, I break that f off into components, and what happens is each components are nothing but real valued function, and for real valued function I am defining, so this is my definition, I am defining the derivative of a real valued function in the jth direction. Okay, so this is, think of it like derivative, it is just the first order derivative in a particular direction, in a one dimensional case. Okay, so derivative, think of it like derivative of fi in one dimension in particular dimension, in particular the jth direction. Okay, jth direction. So this is the idea. Okay, and so that's your partial derivative, and we write it like this. Clear? So once that is there, you see we have that this theorem. Okay, so theorem, I hope the idea is clear. For a real valued function, we define the partial derivatives like this. So basically it is just the derivative but in that particular direction, whatever direction we are choosing. Okay, so let's say, suppose if from omega to Rn is differentiable, okay. So what is the theorem? This theorem will actually guide us to answer this question, that dfx naught at some point x naught, wherever is differentiable, is a m cross n matrix. Now the question is, what exactly is that matrix? Okay, so to do that we define the concept of partial derivatives, and here I am writing this theorem. So if from omega to Rn is differentiable, let's say, and at some point x naught in omega, right, that is given, then what happens is, then the partial derivatives, so this is the relation between derivative and partial derivative, the partial derivatives, sorry, not derivatives, derivatives, yeah, sorry, derivatives dj fi at the point x. Okay, so you see for each fi we have j directions, right? So m directions basically, because j varies between 1 and n. So basically n directions are there, I for each fi, and I is varying between 1 and m, j is varying between 1 and n, right? So I have n j, since j varies between 1 and n, I have n derivatives here, partial derivatives. Huh? Okay, so this partial derivatives exists. Okay, and what happens is, and this is very very important, okay, what happens is dfx, how, and this acting at ej. Clear? dfx, please remember, dfx is nothing but an element in Rn, right? See, dfx is nothing but element of L, Rn, Rm, right? So this is a linear map from Rn to Rm. So basically, and we already discussed talking about linear maps, that you can actually determine the linear map based on how it acts on elements of the basis element, right? So you see, since ei's are element of Rn, the basis elements, okay, so we just want to see what happens to dfx at the point ej, and that, to answer that question, this becomes nothing but summation I equals to 1 to m dj fi, okay, acting at x, acting at ui, okay, acting at ui. Clear? And this holds for j between 1 and n. Okay, so what I meant by this is, you see, if you write down this df, so basically this is acting on ej, and here the end result will be on ui, right? Okay, so essentially if you want to write down what is df at the point x, this is nothing but d1 f1 at the point x dn, okay, the partial derivative with respect to xn, so basically the nth direction of f1 with respect to x, okay. So basically on the first, all the derivatives of the first component and then the derivative of the second component, and in the nth row you will have the derivative of the mth component, so sorry, the mth row. Okay, so d1 of fm of x, dn of fm of x. Yeah, and you do realize that this matrix is a m cross n matrix. It has m row and n columns. Okay, so we have this. So essentially what is happening is this, as a small remark, if f is just a real valued function, if f is from omega subset of Rn to R is differentiable, okay, differentiable, let's say at the point x naught, then df(x naught), okay, is nothing but a, you do realize m will be 1 then, so this is nothing but a 1 cross n matrix, is a 1 cross n matrix, given by, let me write it here only, okay, df(x naught) is f1, not f1, d1 f x naught, d n f x naught. Clear? Okay, and this we will call it, so essentially we will actually, so this is a 1 cross n matrix, sorry, this is a 1 cross n matrix, let me put it this way, 1 cross n matrix. Okay, and what happens is we can define, so one defines the gradient, okay, gradient of f, in this case f is from, gradient is defined as this, gradient of f at the point x naught, these we identify with this matrix, okay, df x naught. Clear? And the gradient will be a function, and and the gradient of f at the point x naught we identify as this d1 f x naught, dn f x naught. So basically this will be a vector in Rn. Okay, and why this identification is there, let me just put this part together. So you see this is there because of this theorem, that let's say let T from Rn to Rm is a linear transformation, then what happens is it is actually nothing, you can actually represent, then there exists a vector, okay, let me put it this way, Rn to R is a linear transformation, then there exists a unique vector, unique vector in Rn such that one can identify that T of x, okay, unit vector, let's say x naught in Rn, let me put it this way, unit vector x naught in Rn such that T acting at any element of x is nothing but x dot x naught. This holds for all x in Rn. Okay, what is the proof? Let's quickly look at the proof why this works. See, for any x in Rn, what happens is x can be written as summation xi ei, right, I equals to 1 to n, and then that will imply that T of x is nothing but summation xi T of ei, linearity 1 to n, and then what happens is you can actually write it as x1 xn dot this vector T of e1 T of en, which is nothing but x dot, let's say x naught, where we write x naught to be this vector, we define it to be T of e1 T of en. I hope this is clear. Okay, so this is the idea. So essentially what I am trying to say is this, you see, for a real valued function, whenever we talk about the derivative map, okay, that is nothing but a linear transformation from Rn to Rm. Linear transformation to Rn to R, which is nothing but a matrix, 1 cross n matrix, okay, which will look like this, right? Okay, now the thing is, you see, we define the gradient of f to be the vector. The vector is given like this, exactly the same sort of thing, but this is a vector in Rn. And how do you actually, why can we classify this thing? How can you identify this? Because we know that if you have a linear transformation from Rn to R, then corresponding to this t, okay, corresponding to this t, you have a unique x0 in Rn. So basically, which actually gives you identification for every element here from in L Rn to Rn, you have you have element in Rn. Okay, so this identification is there, and this is what we are identifying it. So basically, let's say as an example, let's just put it down here as an example. If you have a function, let's say f of x1, x2, let me give you a example here. Let's say x1 square plus x2 square, let's say. Let me do it a simple example, half times. Okay, then what happens is, then we of course know df x0, x1, x2 at any point x1, x2 is nothing but, you see, we write it as the derivative. The first derivative is x1 here and the second is x2. So this is how we write it. See, this, please remember, this is nothing but an element of R2, L R2 R, right? And this is the element of R2. Okay, but we identify this. This equals to is basically mean this is identification. Clear? Okay. So with this, let me go back to this original theorem here. So what is our theorem? It says that f is from omega to Rm. Let's say it is differentiable at the point x0. Okay, now we want to classify what exactly is the derivative map. How does the derivative map looks like? So basically, you see, this is a linear transformation. How do you characterize a linear transformation? How do you know what exactly is that? You just look at how it acts on the basis element. So what does it do? It actually gives you this matrix, okay, df given by this matrix. Okay, so let's look at the proof of this thing. This is very, very important. Okay, right. So let's look at the proof of this. The proof is considerably simple actually. Okay, so you first of all you fix a j, and since f is differentiable at the point x, let's say, yeah, and since f is differentiable at the point differentiable at x0, let's say, at x0, one has, or you can write it like this, right? f0 plus t ej. Okay, see, f is differentiable here. See, what is our definition of differentiability? This definition, right? This is the definition of differentiability. So this definition and the definition which I am writing, these are exactly the same definition, is just broken down parts. So please check that those two are equivalent essentially. But what I am meaning to say is this: you see, this h is any direction h in Rn, right? So I will choose a particular direction which is ej. So we can write that since f is differentiable at the point x0, we can write it as f of x0 plus t ej minus f of x0. So this is h in that direction. So basically I am choosing a particular direction. So this is nothing but f prime x0, let me write it this way, df at the point x0 acting at the point t ej plus a remainder term, right? Remainder term which depends on t ej. Clear? If you break down that definition, you can just write it down. So if you are not convinced, you please check that these two definitions are actually equivalent. Clear? So so what is remainder term? The remainder term is r t ej. So you remember the norm of this is by t, that should go to 0, right? So this by t goes to 0 as where this goes to 0 as t goes to 0. So this is exactly the same definition. I am just writing it in this way. Now you see, since f df x0 is linear, since df x naught is linear, this is nothing but t times df x naught acting at Eg, right? So essentially I can write it as limit t tends to 0 f of x naught plus t Ej minus f of x naught by, sorry, this is t, this is t, by t. This is equals to nothing but df x naught acting at Ej. Clear? Now you see, you just represent f in terms of components, okay, and what happens is then this you can write it. So since f is in terms of components, so basically f is f1, f2, fm, right? Okay, so you can write it as limit t tends to 0 summation I equals to, sorry, summation I equals to 1 to m fi of x naught plus t Ej minus fi of x naught by t acting at Ej, right? So this is, we know, sorry, not acting at dot t uj, that is, this is nothing but df x naught acting at Ej. Clear? Okay, so breaking it into components, one gets this, and which is nothing but our assumption. So you do realize what I am trying to say is this, although it is a derivative, is nothing but a matrix. Clear? Okay, so that is there, and just before I finish, you see, I need to know the concept of, we need to know the concept of continuous differentiability. So what is it? Continuous differentiability. It is nothing but when the function is a differentiable function, you are looking at a differentiable function. So basically a differentiable map, okay, differentiable map f from omega subset of Rn to Rm, okay, this is said to be continuously differentiable, continuous differentiable in omega, let's say in omega, if the map df, right, df is a continuous map, okay, from omega to L Rn R. Okay, so what I mean by this is, see, df at the point x naught, let's say x naught is any point in omega, what I mean by this is nothing but a linear map from Rn to R. This is for any x naught in omega, right? Okay, now I am doing is, what I am doing is this x naught varies in omega, right? So you see, if you are changing, so this df is nothing but a function from omega to L Rn to R. You can think of it like this, right? Now if this function is continuous, okay, then we say it is continuous differentiable. I hope this is clear. Okay, what are some examples? So most polynomial functions, you know, into variables, that is sorry, n variable, or you know, most exponential functions, if you define it like that, using the composition function, you can of course say that they are going to be continuously differentiable. It's not a very difficult thing to prove. Okay, so with this I am going to end this video.